Hi! In this video, we'll be continuing the applications of differentiation. In the previous video, we've talked about a few theorems. You can revise them again by rewatching it. But now, we'll go on to the different tests that we can use when we have differentiation as a tool. The first is we can test whether a function is now increasing or decreasing one. An increasing function means that the function continuously increases. So if a is less than b, then fa is less than fb. And a decreasing is if a is less than b, then fa will be greater or equals to fb. And so if f is continuous and differentiable on the interval, and the gradient is always larger than 0, then f is increasing on the interval. And if it's less than 0, then f is decreasing. And so you can take the idea of like y equals to x squared. The gradient is always positive, so it's like the change is positive, so it keeps increasing. And the proof is we just want to show that we take 2 points, one smaller than the other, the value of the function is smaller as well. So let x and y be 2 points in the interval where x is less than y. By the mean value theorem, f prime c equals to fy minus fc over y minus x. Since f prime c is larger than 0 and y minus x is larger than 0, it means f minus fx is larger than 0. And thus, fy is larger than fx. So, f is increasing. And this is really a good way to test whether a function is increasing one or decreasing one. And so now you can see the application of how we are using the mean value theorem. However, you can see that the converse fails because f prime 0 might equals to 0, but it is still increasing on this function. And so we can only say that if f is increasing, then f prime x is larger or equals to 0, and if f is decreasing, f prime x is negative or equals to 0. And the idea is just to take the limit, and when you take the limit, you need to introduce the equality sign. With that of the increasing and decreasing test, we want to know whether if we now have a critical point, we want to test if f has a local maximum or minimum at that value. And we can use the first derivative test to help us. And the first derivative states that if it changes from negative to positive, then f has a local minimum at that point. And if it changes from positive to negative, then it is a local max. And if it does not change sign, then it is not a local extrema point. We'll prove 1, and 1, 2, and 3 follows the proofs are similar. So we now take that it changes from negative to positive. It means that it's decreasing on this interval and increasing on the other. And that literally just translates to saying fx is always larger than fc to the left of c, and fx is always greater than c to the right of c. This means that fx is always larger or equals to fc for all x in a to b. So c is just a local minimum by definition. And hence, you have now used a way to test whether a critical point is a local max or min. We can see this example for how it's applied. For example, now you have this function, you take the derivative and you determine that these are the critical points. To the left of 0 is decreasing, to the right is still decreasing, and to the right of 1 it's increasing. means 0 is not a local extreme value, but 1 is the minimum point. You can practice on more examples to familiarize yourself with the first derivative test, and watch this video if you do not understand it again. I'll move on now. We shall use a lemma before we move on to another theorem. We'll prove this lemma that says that if the limit exists and is positive, then there exists an interval such that fx is also positive. And this really just stems from the definition of limits. Because if the limit is positive, that means you can find a delta when epsilon equals to L such that fx is positive. That's all it says. So this lemma is very easy to prove, but it helps us to improving the second derivative test. So now you take, if f prime c is 0 and its second derivative is also positive, means it's twice differentiable, then you know that f has a local minimum at c. And if it's negative, the second derivative, then it has a local max at c. So now you can just take the second derivative and determine whether it's positive or negative to determine whether it's a minimum or maximum. The idea is to use the definition of the limit for f double prime c, and this, if you take this as the function gx, it means that gx will be positive in this interval. And so, and since x minus c is less than 0, it means f prime c is less than 0 for the interval, which means that it is a local minimum. Because if f is greater than c, then f prime c is larger than 0. So it changes time from decreasing to increasing, and hence f has a local minimum at c. The same proof goes for the other one, the negative derivative for the second derivative, to prove that it is a local, implying that it's a local maximum. And so this second derivative test gives us a way to find the local minimum, maybe easier than the first. However, there comes a problem that if the f double prime c is 0, the test will not be conclusive, and you can see these counter examples, and then you will have to rely back on the first derivative. So the first derivative always works, but the second derivative has a problem when the f double prime c equals to 0. Now we'll talk about the idea of concavity. And the idea we want to capture is, even though both of these graphs are increasing, their shape looks different. And we say that in this case, it is called concaving up, and in the other, it's called concaving down. And that's when all the tangent lines are below it, but here all the tangent lines are above the graph. But how do we capture these words that all the tangent line lies above or below the graph in mathematics? Well, formally, if we were to draw the tangent line, we see that the value is always less than the graph, and so fx is less than whatever the y value is for the graph. And thus, f is said to be concaving up if fb minus fa is larger than f prime a bracket b minus a for all a and b within the interval, because you can shift this fc over here and then replace the variables. And then, so this is the definition of concaving up, and you can prove its equivalent that if a is less than b, then f prime a will be less than this gradient, and f prime b will be greater than this gradient. It means that the gradient increases and so f prime is increasing. Similarly, for concaving down, it means the f prime is decreasing. And this is the proof for one direction. For the other, we'll now prove it that if f prime is increasing, by the mean value theorem, there exists a c on the graph such that it equals to the gradient of the secant line, which is going to be greater than f prime a, because c will be to the right of a. So a is here, c is here, and since f prime is increasing, it means f prime c is greater than f prime a. And if a is larger than b, f prime c will then be less than f prime a. And the following holds still, that fb minus fa will be greater than f prime a times b minus a. And so, in either cases, f will concave upwards on the interval. A similar proof for when f prime is decreasing, it concaves downwards. And so we can change the second derivative test to saying that f double prime larger than 0, it means that f is concaving up. And if f double prime is less than 0, f is concaving down. And the proof follows here. But again, the converse fails when f double prime is 0. You can read the proof yourself to better understand it, but I hope it's quite intuitive. And with that, we begin to understand now what are inflection points. So we have points that we have shown that how the graph concaves up at certain areas and concaves down at certain areas is increasing and decreasing. And so we want to capture points now that change, where the graph changes in concavity. So an inflection point is defined to be the point where the graph changes its concavity. For example, this graph, it is concaving down over here, but from this point onwards, it's concaving up. And so the concavity changes at here. Similarly for this, and this. And so the theorem goes that if f is twice differentiable and c is an inflection point, and f has an inflection point at c, then the twice derivative at c is 0. And the proof actually follows from the idea of taking the limit from the left and the limit on the right, and for them to be equal, they have to be 0. I'll leave it to you to read, but it's very similar to everything we've done earlier, and so it shouldn't be too difficult to catch. Lastly, with the ideas now that we are able to determine when the minimum and maximum values are using the first derivative or the second derivative test, we're able to tell where the inflection points are. We're able to determine the concavity of the graph. We're now able to use the derivative to determine the graphical behavior of the function. Meaning you're able to picture out how the function will roughly look like, even if you cannot get it correctly exactly. Because you know it's differentiable, it will become continuous. If the derivative is larger than 0, it rises. And you can see this summarizes what we have already done. And now this gives us a way to do a rough curve sketching of a graph to better understand its behavior and use its properties. For example, for the function below, we first determine the critical points to see which is the minimum values. We determine the points of inflection, and we know which intervals it concaves up and concaves down. So we know from negative infinity to 0, it is decreasing and concaving up. So it's this way. It concaves up and is decreasing. From 0 to 2, it concaves down. So we need to draw a graph concaving down. And from the 2 to 3, because we know 3 is a minimum value, it concaves up again all the way to infinity, and it keeps increasing. And so with this graph, we're able to see how it looks like. And that is another application of differentiation. We'll see more application in the next video, and we'll talk about one more theorem that is very important in determining derivatives and limits. Thank you for listening, and I'll see you in the next video.